All right, so you've learned from section 7.1 about how to take Laplace transforms of some different functions. And these, these Laplace transforms, of course, we have the original definition of the Laplace transform, which allowed us to come up with some rules for some general rules for Laplace transforms of some common functions. So like, for instance, a Laplace transform, like looking in the table here, the Laplace transform of t is equal to 1 over s squared. The Laplace transform of e to the negative 3t would be 1 over s plus 3. And that's based on a table given in section 7.1, theorem 7.1.1. Also, if we can take a Laplace transform of a function of t and get a function of s, we ought to be able to take an inverse Laplace transform of the function of s and get back the original function f of t. And you can see here, based on the table, that's what they're doing. So, for instance, the Laplace transform of 1 is equal to 1 over s. Therefore, the inverse Laplace transform, that's in the table there on the top row on the right, the L with the negative 1 power. That's not a power. That just stands for inverse Laplace transform. The inverse Laplace transform of 1 over s equals 1 because the Laplace transform of 1 is equal to 1 over s. Similarly, on the second row, for instance, the inverse Laplace transform of 1 over s squared equals t because the Laplace transform of t is equal to 1 over s squared. Okay, and so you get a once you know a Laplace transform of a function, you can find you know the inverse Laplace transform of a corresponding function of s. And so they have here some common inverse Laplace transforms, and you learn the rules for the Laplace transforms, and of course the table you can use as a reference. And therefore, since we know the Laplace transform of certain functions of t, we can find inverse Laplace transforms of certain functions of s. Okay, so are there any questions on this idea about theorem 7.2.1? About this table? Okay, all right. Well, if you're good with that, let's continue on here. Okay, so they mention in evaluating transforms, often happens that the function of s under consideration doesn't match exactly the Laplace transform given in a table. So we're going to do some problems dealing with that. Okay, we'll get to that. But let's go on here. Let's go on. So if you have the inverse Laplace transform of a linear combination of functions, that's going to equal the linear combination of the Laplace transforms. And again, that idea is based on the idea that the Laplace transform is defined as an integral, and so rules for integrals follow for rules for integrals would follow for rules for Laplace transforms. So like the Laplace transform of a sum of two functions is the sum of the Laplace transform of each function separately. You've learned that. And naturally then the inverse Laplace transforms have to follow the same rule, the same kind of rule. So that this is a natural rule. And again, it comes about by the fact that Laplace transforms are really based on integrals. So rules for integrals follow for Laplace transforms as well. All right, are there any questions so far? All right. So very good. Well, so ultimately, what do we want to do with these Laplace transforms? Ultimately, we want to be able to use them to help us solve differential equations, find solutions to differential equations, and you have learned so far multiple ways to solve differential equations, multiple techniques. Most recently, you've learned power series solutions to differential equations. And Laplace transforms will provide us another way to solve a differential equation. And it's particularly helpful when the right-hand side of the differential equation is a piecewise function. Very helpful in that kind of situation. Naturally, ultimately, then we have to know we have to be able to talk about what the Laplace transform of a derivative is. So, you know, f prime of t is a function of t. It's a derivative. And if we were to take the Laplace transform of f prime of t, that would equal negative f of 0 plus s times the Laplace transform of f of t. Okay, that is that, and the way they do that is they find that using integration by parts. And actually I have that worked out to show you, but I think I'll wait till Thursday's class to show you how to derive this. They talk about how they use integration by parts and get the result, but I can show a few more details on that. But the point is, we can take the Laplace transform of f of t, and the Laplace transform of f of t is going to equal s times big F of s, that's the Laplace transform of the function, minus the function evaluated at 0. And actually, we can also take Laplace transforms of higher derivatives as well. The Laplace transform of the second derivative of a function of t is equal to s squared times big F of s, which is the Laplace transform of the function, minus little s times f of 0 minus f prime of 0. Okay, and again, they can you know, that can be, that's not hard to show. They show it there in the book. You know, finally, the Laplace transform of a third derivative. Okay, you had differential equations, third order differential equations that you had to find solutions for. There's the formula for the Laplace transform of a third derivative, a third derivative of f with respect to t. So, you know, we can keep going and going with this, and there is a general pattern here. There is a general pattern that gives you a general formula for the Laplace transform of a nth derivative of t. There's a general formula there, and well, yeah. So let's go ahead, though, for now. A big F again. The big F means what that means here. I'll show you. So the Laplace transform. Good question, Antonio. The Laplace transform of a function of t is equal, we can denote that by big F, a big function f of s. They mean the same thing, just different notation. The Laplace transform of a function of t is equal to big big function f of s. So when you see a big function f of s, that just means the Laplace transform of some little function f of t.
So the Laplace transform of f is in the Laplace transform of the third order derivative of f? Is that how that?
You mean now going back to the formula?
Yeah.
Okay. Let me go back to the formula here. One moment. So like you're talking, why don't we focus on the first one here, for the
Okay.
first derivative.
Uh-huh.
Okay, so the Laplace transform of f of t, of f prime of t, is
Mm-hmm.
just equal to s times the Laplace transform of f of t minus f of 0. That's how you read that.
Oh, okay.
That's how you read that.
Okay, that makes sense.
Okay, very good question. Very good question. And for instance, for the Laplace transform of f double prime of t, that will equal s squared times the Laplace transform of f of t minus s times f of 0 minus f prime of 0. Okay. You're comfortable with that, Antonio?
Yes, I am.
Excellent. Okay. Are there any other good questions? Okay. Well, then let's go ahead here. And let's see, Zachary has a good question. In the previous formula here for this means the nth derivative. That's correct, Zachary. You're finding the Laplace transform of the nth derivative of t. That's exactly right. And for your homework in section 7.2, which I'll take the password off, and well, I think you'll maybe have some time in class to work on that. That's my hope. But you're not going to have any problems where you have to find the Laplace transform of a derivative, but it will come up when we want to solve a differential equation. We will need that formula. So good question. All right, so let's see here. Let's go ahead. No, wait. Yeah, let's do some examples here. Okay, so let me give you a moment to copy this example down. And it'll be helpful if you have your ebook open. If you have your ebook open to that table in section 7.2, which is theorem 7.2.1. Okay, that's some inverse Laplace transforms. It'll be helpful to refer to that table during the lecture. Okay, but all right, let me give you a moment to copy this example down. Okay, So in this problem, what we want to do is we want to find the inverse Laplace transform of the negative 2s plus 6 over s squared plus 4. So if we look at the, and generally what I do here is I look at the table of Laplace transforms. I don't like to have too many tables, you know, but I mean, I know that if I have a table of Laplace transforms, I can get the inverse Laplace transforms no problem. But I don't see any, like in this table here, I don't see any function that says negative 2s plus, well, I want to say it the right way. I know that these Laplace transforms are going to help, but I got to manipulate this function f of s. And there's a suggestion here. There's a suggestion. Zachary says factor out the negative 2. And I think that's a good idea. As a matter of fact, let's go to the solution. We're going to do several things here.
Can you go back for like a quick second?
Sure. Don't copy this table though. You don't need to.
No,
copy
not
it.
that. Like one more page, please.
Okay. 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 So I agree, Zachary. Zachary's thinking, okay.
Okay, I'm good. Thank you.
Factoring, very good, Matthew. Very good. Factoring can be involved, and also let's break this up here. Let's break this up. So, okay, everybody's good. Matthew's good, and everybody's good. Okay, maybe give me a few thumbs up if you're ready to move here. We'll. Okay, thank you, very good, excellent. Okay, well then let's. So you know you have the tables in your ebook, so you know. Okay, so what I'm going to do, what we're going to do, is we're going to break this fraction up into the sum of two fractions. The sum of two fractions. I mean, we can do that. I can write negative 2s plus 6 over s squared plus 4 as a sum of negative 2s over s squared plus 4 plus 6 over s squared plus 4. We can do that. And then I can factor out the negative 2 on the first fraction. And then on the second fraction here, I have a 6 divided by s squared plus 4. But really what I would like is, you know, being that the denominator is s squared plus 4, well, s squared plus 4 is the same as s plus 2 squared. So I'd really like a 2. I'd really like a 2 in the numerator, but I have a 6, right? I have a 6. Well, what I can do is I can write 6 as 3 times, hold on here. Yeah, 3 times 2. And 3 times 2 is the same as 6 over 2. And so the Laplace transform of 6 over s squared plus 4 is the same as, I'm sorry, the inverse Laplace transform of 6 over s squared plus 4 is the same as 3 times the inverse Laplace transform of 2 over s squared plus 4. And now this allows me then to find the inverse Laplace transforms of the second function, of the second, you know, the second inverse Laplace transform, and I can get the first inverse Laplace transform because s over s squared plus 4 is already in good form. Okay, let me deactivate my email here. I don't want any distractions. Are there any questions on this? I want us to take our time So this of course is the solution here.
Wait, how'd you get to the cosine and sine again? Is that just from the table?
That's from the table. Yes. So for instance, good question. Good question. So let me ask you this, class. What's the Laplace transform of the cosine of 2t? Well, the Laplace transform of the cosine of 2t, k is equal to 2, right? K equals 2. So then that's going to equal s divided by s squared plus 2 squared, right? So the Laplace transform of the cosine of 2t is equal to s over s squared plus 2 squared. How many maybe have that, knew that offhand, maybe have that memorized from the table? So did anybody maybe know that offhand? Okay, Christopher rings a bell. Rings a bell. So, well, that comes from, so let me see, is that, Paige says, is that S? No, okay, this is an S. Yeah, this is an S here. This is an S. Hold on. This is an S. So then the inverse Laplace transform of S, good question, Paige. The inverse Laplace transform of S over S squared plus 4 would then just have to be cosine of 2t. And that's how, that's how we get there. It's all because of the fact that the Laplace transform of the cosine of t is equal to s over s squared plus 4. Therefore, the inverse Laplace transform of s over s squared plus 4 would be cosine of 2t. Zachary, are you better now? Are you better now? Oh, okay, okay. No problem, no problem. All right. Are there any questions so far? Who's feeling good? Who's okay? Who's comfortable? Let me know, and then we'll move on to the next example. Okay, Christopher's good. You have to let me know, please, if you have any questions. Kathy is good. Wonderful. Max is good. All right. All right. Well, she is good. Excellent. Okay, let's look at a next example then. Okay. We want to find this inverse Laplace transform. Let me give you a moment to copy the example down. A, B, C, D, E, F, or G. Which formula is going to be the right formula? Okay, Antonio, you're right. So we know, since we have here on the right here, the Laplace transform of the cosine of kt is s squared over s squared plus k squared. We know that the problem that we're dealing with is similar to that. It's like a cousin or a brother, okay? What we have to do then is manipulate our problem so we can make use of formula E. So what do you think we need to do to this expression here? Okay, all right. Zachary says factor out a 9 or take out a ninth. That's right. So okay, let's do that. All right. So my first instinct is to factor out this 9 here from the inverse Laplace transform. I can factor constants out of an inverse Laplace transform. We can do that. And then in the denominator here, I have 9 times s squared plus 1. Well, I want to get the s squared by itself. I'm going to factor 9 out. So that'll give me 9 times s squared plus a ninth in the denominator. Well, this 1/9 here can be brought out of the inverse Laplace transform. And so now I have 9 times a ninth times the inverse Laplace transform of s over s squared plus a ninth. So the inverse Laplace transform of the fraction 9s divided by 9s squared plus 1 is going to equal then the inverse Laplace transform of s over s squared plus a ninth. Okay, and we know from the table that the Laplace transform of the cosine of kt, okay, that's going to that formula E from the table of Laplace transforms from section 7.1. That equals s divided by s squared plus k squared. Right? And so what's k equal to? What's k equal to then for our problem? A third. Good. That's right, Matthew. And so this is our final answer. The inverse Laplace transform of the function 9s over 9s squared plus 1 will equal cosine of 1/3 t. All right, are there any questions on this example? What we're really doing, ultimately, again, we want to use the Laplace transforms to help us solve differential equations. But before we do that, we got to kind of know the rules of the game and how it's played, the rules of the game. You're learning the rules here, essentially. You're getting familiar with kind of, how these transforms work. Okay, maybe give me a few thumbs up if you're comfortable, and then we'll move to the next example. Okay, Andrea's comfortable. Good, thank you. Christopher's good, wonderful. Max is good, okay. So, you know, we have to do something a little more interesting, right? I mean, this is nice, but let's do something a little more complicated. Okay. I want to find the inverse Laplace transform of 1 over s cubed plus 5s. Let me give you a moment to copy the example down. It says take the 1 over s out and factor. So Zachary, Antonio, and Matthew are saying the same thing. We need to factor that denominator. Okay, well, so then let's go ahead and do that. If we were to factor the denominator, what would the denominator factor as? It would factor as 1 over what? 1 over that's right, 1 over s, and I'm just writing this here. We'll get to the 1 over s times s squared plus 5. But you'll notice in the table of Laplace transforms, I can't really do anything with that function as it is in the form it's in. Can I rewrite that perhaps as the sum of two functions? Maybe the first function over s and the second function over s squared plus 5. Yeah, what is that called, that approach? Zachary's calling it the AB method.
Fraction decomposition.
Partial
fraction.
Well, what did you say, Justin?
Partial fraction decomposition.
That's exactly right. Partial fraction decomposition. And, you know, for Laplace transforms, that's going to be really big. Really big. So let's go ahead and I'll show you so, you know, there's the table. And probably going to use several of these formulas to help us. But, okay, so 1 over the fraction 1 over s times s squared plus 5, we write that as a over s plus bs plus c over s squared plus 5. So the s is a linear factor. S is a linear factor, so we have a constant above that. And then s squared plus 5 is a quadratic factor, and so we have a linear factor above that. Okay, and so what we're going to do, of course, is we're going to multiply both sides by the common denominator of s times s squared plus 5. So maybe I'll just, this is s plus 5 in the denominator here. Well, wait, Zachary, where did bs plus c come from? You mean right here? Okay, so in the denominator, you have s squared plus 5. Okay, s squared plus 5 is a polynomial of what degree? What's the degree of the polynomial s squared plus 5? 2. So in the numerator, then, you put a polynomial of one less degree. So b times s plus c is a polynomial. I mean, we have to find out what those constants b and c are. But b times s plus c is a polynomial of degree 1. You know, similarly over here, you have an s. An s is a polynomial of degree 1. And above that, then, is a polynomial of degree 0, which is a constant a. Zachary, we didn't have to worry. I'm not sure. I think partial fractions, yeah, it came up earlier in the course. But now you're going to be doing partial fractions like big time. Okay, with you all should have seen this in your calculus 2. How many saw partial fractions in calculus 2? I mean, it's something you should have seen for sure.
We never, I mean, we did do partial fractions, but never when the denominator wasn't a 1 degree polynomial or a linear function.
Oh, well, that's interesting. That's interesting, Justin. Well, okay, so now you're seeing it here. I taught calculus 2, and I certainly covered like this kind of case. But you know, sometimes for various reasons, material might not be covered maybe as thoroughly as it could have been. But it's okay. No judgments, no judgments. So what you do is in the denominator, if you a polynomial, you ask what degree is that polynomial. That determines then what you put in the numerator. So s is a polynomial of degree 1, so we put a constant above the s. Constant is a polynomial of degree 0. Similarly, for the other fraction, s squared plus 5 is of degree 2. It's a second order polynomial. So in the numerator, you're going to put a first order polynomial, b times s plus c. Now, what you can do, there are several methods, right, for partial fractions, but generally what I like to do is multiply both sides. Okay, let me just I like things to be looking good. You know, how am I arriving at this equation here? I'm taking both sides of this rational equation and multiplying it by s times s squared plus 5. Okay, s times s squared plus 5. Okay, and obviously you're going to distribute the s times s squared plus 5 to both of these terms here, right? Both of those terms. And when you do that, you'll get 1 equals, because on the left side, the s times s squared plus 5 simplifies out. And so you'll get then 1 on the left side, and on the right side, you'll get a times s squared plus 5 plus bs plus c times s. And that just has to do with simplifying. Now, what I like to do is I like to group things together. So I'm going to I can rewrite this equation, 1 equals a times s squared plus 5 plus bs plus c times s. I can write that as 1 equals the quantity a plus b times s squared plus cs plus 5a. And based on that, I can solve for a, b, and c because, you know, this is an equals, right? This is an equals here. So if the number 1 equals the right-hand side, well, then there's there's no s squared term. In other words, 1, you can think of it like this, and I'm going into a little detail because 1 is the same as 1 plus 0 times s plus 0 times s squared. So therefore, that means then if since the left side equals the right side, that means, well, a plus b would have to equal 0, c would have to equal 0, and 5a would have to equal 1. So like for example, the 0 times s squared, that has to equal a plus b times s squared. And that's why a plus b has to equal 0, for example. So you end up being able to solve for a, b, and c. Okay, and then I can feed back in what a, b, and c are in my inverse Laplace transform. Okay, a, b, and c. Are there any questions up to this stage? Please let me know. All right, well then naturally, I can factor out those 1/5. I can factor out the 1/5 and the -5 from their inverse Laplace transforms. And then I go to the table. The Laplace transform of 1 over s equals 1. Sorry, the Laplace transform of, hold on here, let me go to the table. Yeah, the Laplace transform of 1 is equal to 1 over s, so the inverse Laplace transform of 1 over s equals 1. The Laplace transform of s over s squared, of the Laplace transform of the cosine of square root of 5t would be equal to s over s squared plus 5. So the inverse Laplace transform of s over s squared plus 5 would just be the cosine of root 5t. Okay, and then this is the final answer. You get for the inverse Laplace transform of 1 over s cubed plus 5s, that's going to equal 1/5 minus 1/5 times the cosine of the square root of 5t. Are there any questions? All right, who's feeling comfortable? I'm going to ask that before we move to this last example. Maybe give me a thumbs up if you're feeling good. All right, Christopher's good. Max is good. Okay. I'll sleep better if I get one more thumbs up from somebody. Okay, thank you, Andrea. All right. So I'm trying to do a variety of examples It'll be helpful for that homework on 7.2. Well, let's go ahead to the last example here. All right. Let me give you a moment to copy this example down. Denominator, class. What are we going to have to do to the denominator in order to find this inverse Laplace transform? What do you think?
Factor it.
Factor it. Factor it. Right. We're going to factor that. It factors. It factors. So, all right. Let's go to the next page. Well, let me ask you, what is this factor to? S to the fourth minus 9.
Is it s squared plus 3 times s squared minus 3?
That's right. Good, Justin. S squared plus 3. Matthew agrees. And I appreciate all, Zachary's on the right track here. S squared plus 3 times s squared minus 3.
Could we also factor that second term again?
We could factor s squared minus 3, but I don't want to, because I know there's a Laplace. I think about my table of Laplace transforms, and I have transforms that have, like, in the denominator. Well, I want to be a little careful. Like here, I have, like here, an s squared minus k squared in the denominator. So I'm hopeful that I won't need to factor that term anymore in order to find the right answer. You could do it, though. You could do it, and you would still get the right answer, Justin, but it won't be necessary. Good question. Good question. So, okay. Well, all right. I'm going to factor 1 over s to the fourth minus 9 as 1 over s squared minus 3, 1 over, and the denominator's s squared minus 3 times s squared plus 3. Oh, got to use partial fractions. Got to break this up. And so I do. I have, I'm going to write this fraction as the sum of two fractions. The denominator under the first fraction is s squared minus 3. Yeah, question, Antonio?
Does it matter if you do as plus b over s squared plus 3 or s squared minus 3? Like, does the starting denominator matter, or will you get the same answer as long as you're consistent?
You mean if I had, like, for the first denominator, I had s squared plus 3 instead?
Yeah, like if you're consistent throughout in your final answer, does it matter?
It does not matter.
Okay.
It does not matter.
Okay.
Good question. Good question. So the first fraction, I have s squared plus 3. That is a polynomial of degree 2. So the above it, I'm going to put a polynomial of degree 1, as plus b. Okay, Zachary, now it rings a bell. Zachary, it rings a bell for Zachary. Good, good, good. Very good. And, and so what we're going to do naturally then is we're going to multiply both sides of this. Get Get that looking good. I'm going to multiply by the least common denominator, which is s squared minus 3 times s squared plus 3. Okay, so I'm going to distribute that to the two terms on the right. And on the left, of course, I'm also multiplying by, I don't have a lot of room here, so I have to just kind of fit it in. But I'm multiplying by s squared minus 3 times s squared plus 3. And of course, on the left-hand side, then, I'm going to get a 1. Try to make this look good. One moment. Trying to make that 3 look good, class. Doggone it. Hold on. Very good. That's fine. And we know this is a plus. Okay, so we're going to get then. Let's see here. Hold on. I like things to look good. There we go. Okay, so we're going to end up getting what I did here. I did a little more work. I foiled these two binomials and got this expression, and then I foiled these two binomials here and got this expression. And then I group things. So I have an s cubed term, an s squared term, an s term, and a constant. And by the fact that 1 has to equal the entire right-hand side, that means then that the constant 3b minus 3d equals 1, but the other coefficients for s cubed, s squared, and s, they would all have to equal 0. So you have 4 equations with 4 variables. 4 equations with 4 variables. Now this is really, you know, Paige, you're wondering how I got these 4 equations here? Okay, good question. Let me show you why. So on the 1 here, the 1, okay, I can write that as 1 plus 0s plus 0 times s squared plus, okay, good, no problem, 0 times s cubed. And so, all right, very good. That's correct, Zachary, that's right. Those terms have to be, those terms are equal to 0, and so the coefficients have to equal 0. So what I do is I say, okay, well, second equation here, b plus d equals 0, that means b equals negative d. And I'm going to substitute b equals negative d in the third equation that involves variables b and d. Okay, and so if I do that, if I substitute that in, b equals negative d in the equation 3b minus 3d equals 1, I'll end up determining that d equals negative 1/6. And that means then, of course, b equals positive 1/6. Okay, let me know if you have any questions. Okay, who's feeling may I go to the next page? Are there, maybe give me a thumbs up if you're good. Thank you, Christopher. All right, Matthew, very good. All right, Antonio, very good. Well, now we have to solve for C and D. So the first equation is A plus C equals 0. Well, I'm going to let C equals negative A, and then I'm going to substitute that in the third equation. Right, so A equals negative C. Well, C equals negative A, but A then equals negative C as well. Okay, so substitute that in the third equation, and you'll determine then that 3 times negative C minus 3C equals 0. You'll get then C equals 0, and therefore A equals 0. And now you're able to substitute in your A, your B, and your C, and your D, right? Really quite fascinating. So I could write the fraction 1 over s squared minus 3 times s squared plus 3 as the difference of these two fractions. 1 over 6 times s squared minus 3 minus 1 over 6 times s squared plus 3. And this allows us now to proceed forward with finding the inverse Laplace transform. So the inverse Laplace transform of the difference of these two fractions is just the inverse Laplace transform here of the difference. Let me do it this way. The inverse Laplace transform of the difference of these two fractions is just the difference of the inverse Laplace transforms. And I'm going to factor out as that the 1/6 constant from each. That gets me down here. Are there any questions up to this stage?
Yeah, if it's s squared plus 3 and 3 equals k squared, and this should represent k over s squared plus k squared, where does the k in the numerator come from? Do we have to multiply?
We're going to put it in, Antonio. Good question.
Oh, okay. All right.
Antonio is saying that if we have, well, let me ask you this. Since 3 here in that second inverse Laplace transform, that 3 is equal to k squared. So what would k be?
The square root of 3.
That's right. But we don't have a square root of 3 up here, right? In the numerator, we have a 1. Well, what we're going to do is we're gonna rewrite this second inverse Laplace transform so that we can take the inverse Laplace transform, and we'll do it for the first one as well. So what we'll do, I'll go to the next page here if everybody's good. Okay, so what I did was I rewrote, thank you, Andrea, I rewrote the, you know, what we had here. And what I do is I introduce a root 3 in the denominator and the numerator. Root 3 over root 3 equals 1. So I'm not like changing the expression. I'm just rewriting it. I'm doing a little mathematical plastic surgery on it. I'm rewriting it. Rewriting both inverse Laplace transforms. Christopher's liking that, so that we can we can get then inverse Laplace transforms that in the form that will agree with our table. Okay, that the whole really the work we're doing here is really work so that we can rewrite these, so that we can get inverse Laplace transforms that will that we can find, and we have to then, so we have to rewrite our original problem. That's all you're doing. It's just a rewriting. How many think? And then we end up getting the, you know, the final answer. Now we take the inverse Laplace transforms, and one of them is going to be the sine, the hyperbolic sine of root 3 times t. The other is going to be just the sine of root 3 times t. And that's really, I mean, that's the answer. And that's, how many think, I mean, I think these are, I mean, I don't know, how many find these kind of fun? I mean, I think it was kind of like little puzzles. All right, Antonio's liking it. Does anyone else think these are fun, kind of fun? I hope more than Antonio and Matthew like them. Well, Matthew likes them too. Is there maybe a third person who thinks they're cool? Okay, thank you, Christopher. Oh, okay. Andrea's sort of yay and nay, more or less, más o menos, right? More or less. Well, you know, so that's really, you know, thank you for the responses, and that's really what section 7.2 is about. And I think you're going to be fine. I don't think that assignment's going to take that long to do. And are there any questions before we stop here? Okay, Christopher's good. Excellent. All right, everybody's good. All right, let me stop the recording.